So let's speak about mathematics. One of the most fundamental abstraction we use in mathematics is the concept of number. We can count things, we can count quantities, we can use numbers to measure various objects. Speaking for instance of myself, I have a certain height, I have a certain weight, I have a certain results of my university and school exams. And we can take all those numbers, group them together, and we'll get a vector of numbers that characterize certain aspects of myself. For example, suppose we only take my weight and my height as a characterization of my person. So I will be somewhere over here, and the x-coordinate of that point that represents me will be my weight, and the y-coordinate will be my height. And obviously, if there are more coordinates, the points that characterize me will be living in a higher dimensional space. My area of expertise is computational topology and topological data analysis. What we are trying to do is to understand the overall shape of a collection of points, or point clouds as you wish, where every point characterizes certain objects. We may, for instance, try to understand what is the shape of points where every point characterizes the weight and the height of a person in a given population. Let's concentrate on a simple example. Over here we have a collection of points that are sampled from a circle with a certain noise, and we want to use tools from topological data analysis to understand them. What I will present over here is an idea of a ball mapper algorithm. It is my recent algorithm that I used to understand shapes of high-dimensional point clouds. And the idea is to cover our points with an object, with a sets or cover elements as you wish, and all the points within every cover element will be considered similar. For instance, the point covered by the rectangle on the left hand side will be considered similar, and we'll be adding cover elements as long as every point is being covered. Now, once we are given a cover, we can forget about the point clouds underneath and just look at the cover elements. And by looking at those cover elements, we will create an abstract graph that encapsulates the shape of the initial point cloud. So a shape of a collection of points sampled from a circle. The vertices of those graphs will correspond to the cover elements. So we'll have one vertex per a cover element. And we'll put an edge between two cover elements, or between two vertices, if the corresponding covering elements intersect. And by doing so, we'll get this graph. We can forget about the cover, and we will have a graph that will give us a representation of the underlying shape. So let us see how this methodology works for much higher dimensional data that are a little bit less trivial than a collection of points sampled from a circle. This is a lucky cat. It's a famous Chinese sculpture that you can see in many places in China, in most of the Chinatown. It's supposed to bring luck. So suppose I take a sculpture of a lucky cat, put it in the middle of my room, and take a picture of this lucky cat from many different angles, uniformly, by moving around the sculpture. And what I want to do then is to take the pictures. In this example, every picture is quite low resolution. It's 128 by 128 pixels. And what I want to do is to linearize that picture. What do I mean by that? Let's concentrate on this very simple 3x3 image. What I want to do is to create a vector of numbers based on that image. And please keep in mind that every of those pixels will be storing a gray level value, because in that example we are taking black and white pictures. So instead of 1, 2, 3 all the way to 9, we'll have certain levels of gray between 0 and 255. And those numbers over here are only to track, for us to track, how the linearization procedure will work. So I'll take the pixel number 1 first, followed by the pixel number 2, 3, all the way to pixel number 9. So I'll take the first row of the image, followed by the second row, followed by the third row. And by doing so, I'll create a vector of 9 numbers, or a vector in 9-dimensional space that characterize this picture. And I will do the same for every picture of the Lucky Cat. In that case, we have pictures in 16,384 dimensional space. And altogether we took 72 pictures of the Lucky Cat, so we have 72 points in the 16,000 dimensional space. And we'll use the same methodology to answer the question, what is the shape of this collection of points? Now, what we have indeed is a file where every line corresponds to a single image, and we have 72 lines in this file. What we can do is to upload this data into the software which I have created, and we'll get that image. We'll get an image of a circle, and every circle inside this big circle corresponds to a covering element. The circles that are larger are covering more images. The circles that are smaller are covering less images. Let me explain that intuition is that this is quite obvious to understand that we shall get a circle while taking a picture of a Lucky Cat. So suppose we are starting by taking a picture from the front of the Lucky Cat. We'll get a certain vector. Now, once we are moving clockwise around the cat, we are getting more and more different images, and we'll start to see a picture which is similar only after we make 360-degree turn around the Lucky Cat. And once you actually translate it into understanding of points in the 16,000 dimensional space, well, that really means that we are starting from a point, we are moving away from it, and after a while we are coming back after taking these 72 pictures, but we are coming back from a different angle, from a different side. And by doing so, we are closing a loop. There is one more piece of information we can read out of that image. Namely, on the left-hand side, the covering element seems to be larger. And we can actually go back to the data and understand that the elements on the left-hand side correspond to the back of the cat, which is much more uniform. You really need to move quite a bit in order to see a difference once you are looking at the back of the cat, compared to the case when you are looking at the front of the cat. And that's why we are covering much more ground on the left-hand side than on the right-hand side. Okay, well, we see that this methodology is bringing some interesting information. Let's try to see how it can be used in economics and political sciences. And for that, I will take the data from UK constituencies. There are 650 constituencies in the UK, and for each of them we have a certain data. Namely, we have 2011 census data. So we understand a lot of socio-economical variables for every constituency. To be precise, we have more than 100 variables characterize the wealthiness, the level of education, and many other socio-economical variables per each UK constituency. Out of this more than 100 variables, we actually selected 14, which varies the most across the country. And we decided to run it through the same procedure. to understand the shape of the UK constituencies according to the UK 2011 census data. And this is a collection of 630 points, because for some reason the constituencies from Northern Ireland are not counted, in 14-dimensional space. And we see this shape, which has kind of a heavy center and a few outliers, or flags as we call it. And that's the shape of the socio-economical variables for most of the UK constituencies. And let me go back to school mathematics this time. So the classical thing we do in schools is to plot functions. Once we have x, we can plot f of x, where, for instance, in this case, x is a linear function. Now the question is, can we plot variables on the top of much higher dimensional space, where our x is not just the real line, but in fact something like the 14-dimensional summary or the shape of the data? And indeed, we can do it. So coming back to the idea, every cover element in the constituency case cover a number of constituencies. Now, if we have a variable per constituency, what we can do is to take an average for every cover element of those variables. So let me speak about the result of 2016 Brexit referendum. So right now, for every constituency which is covered by those cover elements, I am taking an average result of the vote in 2016 referendum. And we see that the constituencies that support Brexit are the constituencies in blue. They are quite concentrated, while the constituencies that support to remain in the European Union are quite spread across this multi-dimensional space. Now, there's an obvious question, given the incoming elections in the UK. If we actually, instead of plotting the result of 2016 Brexit referendum, we plot the result of 2015 election for a Conservative Party, we'll get a picture like this. Or for the Labour Party, we'll get a picture like that. Keep in mind that in that case, a scale is a bit different. A scale, the coloring scale, is telling you how much a given party is winning or losing compared to the winner in a given constituency. Looking at that picture, we can understand better various political strategies, various political decisions. And this is just one of the examples of the use of topological data analysis. And it is a universal tool that allows you to understand your data, the shape of your data, no matter what they are. Because data very often have shape. Shape have meaning. And meaning brings understanding and allows you to bring value into your data.